All right, we're going to finish up kind of circuit review, right? And again, you all have to let me know if this is not stuff that you've seen before, because, I go on the certain assumptions that you may or may not have seen all this stuff. We might have a slightly different approach. We might be giving you more information like when we did the super mesh and the super node discussion. But I'm hoping that none of the stuff that we've done thus far is new. It's all review. But this stuff is probably also review, except towards the end. And again, the whole concept of Thevenin and Norton, and again, you all know about Thevenin and Norton, is really just to simplify a lot of future circuit analysis, right? If we can find Thevenin and Norton equivalents, which basically tell us I can have this incredibly complicated circuit with millions of different components, and as long as I replace that with the proper either Thevenin or Norton equivalents, it doesn't matter if I have 10 million circuits or those 10 million elements or those two elements, the circuit's going to respond the same, the external circuit that you apply to it. So one of the things that we as teachers don't do a good job of explaining is what is the purpose. It's to replace this really complicated circuit with a very simple circuit. So when you start putting stuff on it externally, you can monitor what happens externally to see, all right, how does that impact the circuit? Okay, so you really are just going to simplify things down quite a bit. In real world, do you do a lot of Thevenin and Norton? Absolutely. One of the things, if you take a class from me called Power Systems Analysis, we actually determine what the fault current can be at any specific location just by knowing the pre-fault voltage and the Thevenin equivalent. So I can model the really big, complicated utility system with millions and millions of pieces of equipment, and I can tell you what the fault current is going to be at a specific location. So that's why we do a lot of the stuff here. So if you look at the Thevenin equivalent, you're replacing a circuit that I don't need to know specific information about. You're replacing this whole network of stuff with one voltage and this is the other important thing, series resistor. So that complicated network is accurately represented by two elements. And then I just put load on it or other additional components to go ahead and do whatever analysis that I have. All right, so you can do all kinds of source transformations. As you see in the first case, right, we have network A and network B. We really ignore network B. And how do you ignore something? You open circuit it, right? So when you open circuit it, you are essentially not including it in the circuit. Plus, the Thevenin equivalent says, from the perspective of the outside world looking in, find the Thevenin equivalent resistance and the open circuit voltage at those two terminals. So you can apply an open circuit for finding Thevenin equivalent because that's the definition of what a Thevenin equivalent voltage source is. So let me get this out of the way. So you can see on the first circuit, I can convert this to a Norton equivalent, right? I can take that 12 volt and 3 amp and essentially 12 volt and 3 ohm, sorry, and essentially do a source transformation, which is another way to say Norton equivalent, by just dropping a short circuit across the terminal, right? Then I solve for this current, which is just going to be 4 amps, right? And then the resistance is whatever the resistance is going to be seen externally by replacing all the independent power sources with their equivalent internal impedances. Remember, a voltage source is a short circuit. So this is going to become a 4 amp supply, and it's going to be in parallel with a 3 ohm resistor. So that whole those two circuits can be represented by this right here. Okay. Or actually, let's go over here because that's step B. Now I've got one source here, and I've got two resistors here. These are clearly in parallel with each other, right? So I can do a parallel combination, product over sum, 18 divided by 9 is equal to 2. I end up over here. And then my last step is go ahead and do an inverse source conversion, go back to the voltage source. So the same thing over here. I have a current source here, 4 amps, 2 ohms. I solve for the open circuit voltage, which hopefully what you see is plus or minus 8 volts. And then I've got this circuit here. Now I've got these two elements in series with each other. I put those together, and my Thevenin equivalent is 8 volt in series with a 9 ohm resistor. That's a lot of work, though, isn't it? Not a lot of work doing source transformations. I found it to be a lot of work because I've got like intermediate steps where why not, my suggestion is, why not go ahead and figure out, is there anything I can do with this first circuit? Let me make sure I have whiteboard up. I don't. So let me copy this part of the circuit here, bring it over to whiteboard. And paste it over here. And so now what I can do is, because I'm looking for the Thevenin equivalent, I know that I have plus minus 12 volts, 3, 6, and 7, right? These are open circuited on the terminal. So how much of a voltage drop am I going to get here? 0. So this voltage here, V6 ohm, is the open circuit, isn't it? So if you can quickly look at that circuit, I can see V6 ohm is 12 times 6 over 9. Isn't that equal to 8 volts? I can do that in one step. Don't have to do a lot of additional work. Notice I did not throw away the 7 ohm resistor. Perhaps you were taught in the class, oh, there's no voltage drop. I can ignore the 7 ohm resistor, which means you get rid of it, right? You don't even include it in the circuit. Is that appropriate to do here? Why not?
No.
It's not. Why not?
Because when you put a load on it, now current is going to go through that 7 ohm resistor.
That's true, but it didn't affect the voltage. So if I'm solving for the Thevenin equivalent, would I include it? And the answer is, I'm only looking for open circuit voltage, but what I'm looking for from the Thevenin equivalent is the actual resistance of all those elements in series and parallel. So my circuit then becomes, here's my 7 ohm, and I'm looking in through here, right? But I got to figure out how to take that 3 ohm resistor. So I replace the 12 volt source. Go ahead. With a short internal equivalent impedance. It is a short circuit. And now I see that I have 3 in parallel with 6 plus 2 equals
Plus
7 equals 9 ohms. So I want to warn you, because this is what previous classes have made a mistake. That resistor doesn't matter, so I can throw it away. I didn't do that, right? I said that this is plus to minus 0 volts. So it won't impact the voltage that's seen, the open circuit voltage. So you can ignore it when you do the circuit divider, the voltage divider circuit, but you can't ignore that 7 ohm resistor when you're calculating the Thevenin equivalent impedance. Okay? That's kind of a small thing, but it's a very important thing, because a lot of students just say, well, I can throw that 7 ohm resistor because it's not including in the circuit because it's open circuit. Okay, so you can do whatever you want. Like I said, there's many ways to skin a cat. So you can go ahead. So you disconnect the load. This is what I recommend. Find the open circuit voltage and then solve for R equivalent by turning off all independent power sources. That's usually the fastest way to do it, because we're all pretty good at doing series parallel combinations when there are no power supplies in our circuit. But I don't recommend simplifying your circuit down because we're all really good now at KVL, KCL, right? We can always go to KVL and KCL. Even if this circuit was more complicated, we could still solve for that open circuit voltage. We would just have to come up with something else, some other approach. All right. So this is the same example. I don't know why I put it back over here. Well, actually, I know why, because we just went ahead and did the same thing, right? We saw we can solve for the plus to minus V6 ohm here. 6 ohm, not 6.2. And then we can do that same approach. Very, very efficient. Very, very easy to do that. How about Norton? Norton's the same approach, except we're solving for current. All right. You will most likely use Thevenin equivalent in the real world as opposed to Norton, right? And it's not anything other than when I'm doing a calculation, if I have this, right? So this is V Thevenin and this is R Thevenin. Now when I put a load on here, there's a box, that's pretty easy to calculate the voltage and the current. When I have a parallel circuit over here, and I put something over here, it gets a little bit more work. It gets a little more confusing for students to do that. So people tend to like working with more Thevenin equivalents. Like you'll find voltages way more than you'll find currents in the real world. But it works just the same. And R Norton and R Thevenin are exactly the same. So the approach to find either one they're exactly the same. There's no additional work that you need to do. As you can see, the Norton current is just a short circuit current. That's all it is. So when we were doing our circuit up here, we would take the load out and then tack on our short circuit and then solve for I Norton. Okay. So you can see if I had to solve for I Norton in here, in this particular case, it would be a little bit more work to do that, right? But here's the nice thing about doing Thevenin and Norton. You find one, and then you can find the other one just as easily, right? Like I solved for the open circuit voltage here as the Thevenin equivalent. If I put a dead short circuit across here, I will get I Norton, won't I? That's the whole thing about having them equivalent to each other. So you can decide, is it easier to solve for V Thevenin or is it easier to solve for I Norton? And how do you decide? Look at the overall circuit. Sometimes it's easier to put a short circuit on the load and then, or short circuit the load out and do your calculations because you might have a couple loops and it may not necessarily be as obvious. Like the fact that this was a plus to minus 0 volts drop is not a hard thing, but a lot of students, when they're first understanding this process, will forget that and they don't include that. And so they get confused about that. And so that's the source transformation. You can go back and forth and they are equivalent to each other. They are the same. No change, no ifs, ands, or buts. All right, 5 minutes. Find Thevenin and Norton equivalents of the network faced by the 1K ohm resistor. So if you're not sure what that means, you can ignore that as part of your Thevenin and Norton. You can use whatever you want. There, I took the load out, so it makes it even easier for you. If you see it, there's an extremely, extremely easy way to do this one. So easy. If you don't see it, it might be harder. While you're doing that, I'm gonna go blow my nose because I'm still hacking away. I'm sorry. Doozy of a cold. Couple more minutes. Or is everybody already done?
I have a Norton equivalent.
That's okay. You can do Norton. Remember, you get to pick. That's a nice thing about being upper class folks is you are getting to the point with your circuit analysis that whatever you're more comfortable with, you can generally do those things unless like we're trying to do a specific like, hey, I want you to write mesh equations or something like that. But in reality, you really can pick whatever you're most comfortable with. But there are some analyses technique that like I do my class, I do everything in nodal analysis because you almost can't do it with mesh analysis. It's just not practical. So we do nodal analysis for that, but you can do everything you want. One more minute and then we'll see anybody brave enough to put their work up here.
I'm brave enough to ask you, hey, does this look right?
You're brave enough to ask? Well, how about with this? You can discuss what you did and then we'll share it with our people in TV land. And then we'll go from there. And your classmates can critique you. How's that? Constructive criticism, not negative criticism.
Paul, I started by shorting those terminals.
That's perfectly fine. You're perfectly allowed to do that.
Then I did a quick and dirty nodal analysis that I called it VA between the 2K ohm and the 3K ohm to find the voltage. And then I found the current going through the 3K ohm, and then I based my equivalent off of that.
Yeah, I think that's fine.
But, you know,
If
All
you
right.
check, if you check
Go
the
ahead.
chat, my answer.
That's okay. Well, we have a classmate here. What did you do for yours?
well, I pretty much removed both the voltage source and the current source to find the equivalent of the resistance, which gave me the 5K ohm.
Okay, so I think most people, if you want to do that, that's fine. So he started by doing his R Thevenin. And so he had a 2 ohm and 2K ohm, sorry, and a 3K ohm, correct? And then you said you removed the two power supplies. How did you remove them?
I shorted out the voltage source and I opened the current source.
Yeah, okay.
And then that from the load resistor area, if you put an ohm meter across, looks just like a 2K and a 3K ohm in series. So it's 5K ohm of resistance.
Everybody agree? All right, so everybody probably had no problem getting the 5K ohm. What did you do to get either the Norton or the Thevenin, your pick?
That's where it got confusing.
Okay. We heard about Arthur, what he did, right? Arthur, if you didn't understand what he did, tell me if this is embarrassing you, Arthur. That's not my intention.
No, you can pick on me. It's fine.
It's not picking on you. It's just showing you your approach or showing the class what you did.
Yeah,
think
I ended up with 8 milliamps, and it's in parallel with a 5K ohm. I don't know if that's right, but that's what I got.
this is Arthur's approach. And then he calculated I Norton by doing nodal analysis, correct?
Yes. And I defined that bottom node as the reference node.
Yep, that's perfectly fine. So we had one agreement with Arthur's approach. Anybody else okay with Arthur's approach? Nobody?
I'm good with it.
You good with it?
So,
Did anybody have a different approach? I have a different approach.
okay.
Because I'm lazy. Remember?
Yeah.
The idea here is to get it done as efficiently as possible. Remember when you get out of industry, you're going to be billing out at like 200 bucks an hour. They bill me out at 225 an hour when I do consulting. And I'm considered like cheap. So, you know, that's crazy, but that's what you're going to be billing out at. So you're going to do things fast. So I like Arthur's approach. It's really good, except, whoops, fell asleep here. Except one thing. He did too much work. Can I still do nodal analysis on that node? How much current is flowing through here? If I find the Thevenin equivalent voltage, then V1 equals V Thevenin. Isn't that easier? I have one less thing to calculate or include in my calculation. Because what I see is current into the node, 4 minus V1 over 2K equals 2 milliamps. We'll solve for V1. So V1 is going to be equal to 4, let me back it up here. 4, well, that one little thing messed up my brain, it seems like. 4 over 2K minus 2 milliamps. Right, I move the V1 to the other side, then I subtract 2 milli from both sides. So 4 divided by 2K is 8 milli, right? So that's 8, not 8 milli. Oh, no, wait a minute, this can't be right. I did it incorrectly.
I thought the current source was 2 amps, not 2 milliamps.
I gotta multiply by 2K, yes. So this whole thing has to be multiplied by 2K, which means I have 4 minus, isn't that 4? can't be right. I'm making a mistake with my math. Let me do it more accurately. So
Is
4 over 2K minus V1 over 2K equals 2 milliamps, right? So 4 over 2K equals 2 milliamps plus V1 over 2K, correct? And then I'm going to bring my 2 milliamps to the side. So 4 divided by 2K minus 2 milliamps equals V1 over 2K. V1 equals 2K times 4 over 2K minus 2 milliamps, right? I have that correct?
0.
0. So what's wrong with this approach?
I think that the source is 2 amps, isn't it? Not 2 milliamps.
2 million.
It has to be 2 milliamps, right?
I thought up above it was 2 amps in your printed version. Oh,
2 milliamps, right?
2 milliamps. Okay, my mistake. I based mine on 2 amps, by the way. So
Oh, you're based on 2 amps?
yeah, I did. I'm sorry.
That's okay. So what happened here? Both sources canceled out? Well, we know we have to have 2 milliamps going there and then 2 milliamps coming in, right? So the voltage can, in fact, be equal to 0 here, but that doesn't really give us the Thevenin equivalent, does it? So here's a problem with doing some of the approaches. When you end up with 0, you're not going to get necessarily a valid approach. So doing nodal analysis is probably the better way to go because I can't have a Thevenin equivalent equal to 0 because then it's turned off, right? There's no connection to it. So we know that that can't be the case. So we're going to do Arthur's approach, which is nodal analysis because it's the easiest one. And now we have one node, right? Still. So we have current in, current into the node equals current out of the node. So 4 minus V1 all over 2K is going to be equal to 2 milli plus V1 divided by 3K. Yes, no? So let's see. I guess we'll keep it out. So 4 divided by 2K is 2 milli minus V1 over 2K equals 2 milli plus V1 over 3K. I'll bring my V1s to the same side. So 2 milli equals 2 milli plus V1 times 1 over 2K plus 1 over 3K. So those will cancel out. So 0 equals V1. Oh, Arthur's approach didn't work either. So what do we do? Can't have 0. Why can't we have 0? We know we can't have 0 because it's impossible that if we put a load on here, we know for sure that we're going to get some current flow through there, right? If you don't believe me, we just do the nodal analysis with a 1K ohm resistor. We know for a fact we're going to get some value there.
Did you short the end of the 3K to the reference? Because I defined the reference on the bottom node and I shorted that. Then
That's what I did.
Oh, okay.
That's why over here, right, you can see it's V1 over 3K. Go ahead.
You sold individually
Sir.
each source, like solve for the voltage source.
You could try superposition. That's one way to do it. Yep. Superposition would work. Any other thoughts? I think somebody from PB Land was going to start talking too, but I might have interrupted
Yeah,
them.
I think Yeah, my mic keeps cutting out for some reason, but I think I got an easy way to do it.
Okay, fire away.
So you turn the 4 volts with the 2K into current source equivalent. So you
Yeah.
get so you end up having two 2 milliamp current sources in parallel that you can add together. So you have 4 milliamp current source in parallel with 2K, and then you just turn that back into a voltage source and you get 8 volts with in series with the 2K and 3K in series.
So he has a circuit that does this. Is that correct? It's a little hard to read. That's 2 milli, 2
Yeah.
milli, 4K. Would that work for us?
I don't see why not.
Yeah, you've got your new circuit looks like this, right?
By the series for our program.
Yep. So yeah, you can certainly do that approach. And sometimes, right, Thevenin and Nortons aren't always going to work for you, like doing those approaches. So sometimes you have to be a little bit creative to do things. Another option is, and that's what we basically did here, right? You did the source transformation and you did the values that way. I'm not exactly sure. Oh, they ended up with a 1.6 because this is the Thevenin, right, which Matt just showed us. And this is the Norton, which is another way to do that, right? You also could apply a test voltage or a test source. And we'll see how to do that once we get through some of the stuff with dependent sources. So if you have a dependent source, what do you need to do? Well, I've got a Vx over here, right? So I can solve this circuit. I can solve it first for V Thevenin, solve it for I Norton, and then my R Thevenin is just going to be the division of those two, right? So when you have dependent sources in your system, you can't turn those off. So there's no way to solve for R equivalent by doing series parallel combinations, right? So if you can't turn one of the power supplies off because of the dependent source, you've got to do that approach. So this is the first one where we have a case. You want to do this one in class, actually show you how to do Thevenin and Norton. Would that be good practice? Okay. Let's copy this one over in the whiteboard. So let's paste it. And I think I cropped off part of the 4. So we'll just write a 4 there. Yes. It's just an infinite whiteboard. And you can zoom in and out. You can move around. The thing I don't like about whiteboard is like if you zoom, because like you can zoom in and out, you can see sometimes like it's not like a piece of paper that you're limited. So OneNote is sometimes better, like because it stays on a page. But I don't know, like it just seems like this one is a little bit with some of the editing features is a little bit nicer than OneNote. So I think John uses OneNote because it keeps it to a page. But I don't know, I just like the editing stuff here. Like you can use a ruler. There's a ruler bar here. And I don't know if there is one on OneNote, but you can insert the ruler. Where do I put the ruler in here? Maybe I have to bring it up over here. No. Yeah, like you can specify a line and you can actually specify, it doesn't seem to be working so well, but you can actually specify things at angles and you can go ahead and draw perfect angles if you want. But yeah, it's a free product from Microsoft. All right, so let's solve for V Thevenin first. So let's do the same thing we did before, right? Which is, let's just do nodal analysis. We'll call it V1. And we know that V1 is going to be equal to Vx under the Thevenin equivalent case. So let's see, we have the current in here going in. So we have 4 minus V1 over 2K plus Vx over 4,000 is going to be equal to 0, but we already said that Vx equals V1. So we have 4 minus V1 over 2K plus V1 over 4K is going to equal 0. Let's factor out. So we have V1, 1 over 4K minus 1 over 2K is going to be equal to negative 4 over 2K. And now we'll do common denominator. And you can do common denominators when you're subtracting. Don't get nervous. So the common denominator we have here is 4K, right? And what we see is we have 1 minus 2, so negative 1 equals negative 4 over 2K. The negative signs will cancel, so V1 will equal 4K times 4 over 2K, which is equal to 8, right? Not right? Got quiet all of a sudden. Just algebra, right? And when I do that, you can see that I'm trying to keep everything in there and do a lot of, like I said, I've spent the whole summer doing 5th grade math with my oldest son, so some of the stuff you just remember it because I just did it this summer. So he probably was like, "Oh my God, what are you doing?" I was like, "Yeah, you just do it." So everybody got it? Can we proceed? All right, so we got 8. Now let's go ahead and do I Norton because we can't get our equivalent. So we'll do the same process we just did for 2K, our dependent source, 3K, and now I'm going to short that out. Well, plus to minus Vx is equal to 0, right? Because of the short. So this contributes how much current? 0. So now all I have is just one loop to solve for I Norton. So I Norton is equal to 4 divided by 5K. Make sense? Don't make sense? Again, you immediately start laying out the circuit like, hey, let's immediately start going to nodal analysis because that's what we did before. But if you can slow down and realize that there's no current going through there, and no current going through there does not mean a short circuit, does it? No current going through there really means it's equivalent to an open circuit. So don't think that you can replace that with a short circuit. You cannot. Go ahead, Luke.
Sorry, but where did you get the 0?
Because the controlling variable for our dependent source is right here, right? It's looking across the terminals of that element. We just shorted out the element. So what will the voltage be across that circuit? What will Vx always be in the Norton case? 0, because of the short. So that driving voltage for that current source is 0, which means the current source is 0. Okay. So now my R Thevenin or R Norton is 8 divided by 4 over 5K, which is really equal to, let's see, we can invert and multiply. 8 times 5K over 4, which is equal to 10K. When you divide fractions, you multiply by the reciprocal. I did that a lot this summer too. So that's my R Thevenin.
Change.
Keep what?
Change what?
Keep, change, flip. What's that?
You keep the first fraction, keep the same, or no, change the sign. I don't remember how, it was for dividing fraction.
Yeah, you keep the first fraction and then you change, like the division sign the multiplication and then you flip around the
Right.
second fraction.
You all went back to 5th grade. Look at you.
So how does the dependent source affect the R Thevenin?
How are you gonna calculate R Thevenin by doing series parallel combinations when you can't turn it off? If you tried to turn it off, right? Here's our original circuit. 2K. We can replace that with a short circuit. This is 3K. What do we replace the dependent source with? By turning it off. You can't turn it off. You can't replace it with an open. You can only do independent sources, not dependent sources.
So how does that affect the R Thevenin?
Well, you can't do this approach. You can't just short and open things anymore. You can't do that. So it's not permitted to do the series parallel combinations. So we got to do this way. Which, oops. I think is what we did. 8 volts, 10K ohm resistor. Checks out with our work. Pretty cool, right? Bet you didn't learn that when you were doing circuit analysis the first time. So it's review, but we're pushing a little bit of new topics, right? It's not hard. It's just looking at things slightly differently. If you can't do V Thevenin and I Norton because you're ending up with zeros for whatever reason, then just put a test source on there. Plug in a test source at the terminals, because if you tried to do that over here, where you have 1.5 I, if we short this out, what does I Norton equal? This is I Norton, right?
Ooh.
But the problem is, you're not going to get 0, right? That does not equal 0. But this, if you open circuit this here, what does I equal now?
0.
0. So then you would end up with no voltage source here, which would mean V Thevenin equals 0. So 0 divided by I Norton, you can't have an R Thevenin equal to 0, right? So all you need to do is a test source. And you can pick whatever you want it to be. It can be a voltage source or a current source, but make it an easy one. Make it a 1 volt or 1 amp current source. So the reason being is because if I have a 1 amp source here, if I can calculate V test, so if I calculate that, then R Thevenin is V test divided by 1, which just means it's the test voltage, isn't it? So it's really easy if you use 1, because if you use this as a voltage source, then it would be 1 over whatever the value is. So then you just take the reciprocal of it and you got the answer. All right, so let's do this one with a test source. Okay, so that was 5 ohms, I think. No, 3 ohms. So we can't do the approach to solve for Z Thevenin, right? Because we have a dependent source here. So we're out of luck. So you need to solve for V test. It would seem to me that if I do nodal analysis, I've got V1, which happens to be equal to V test, right? Not right? So let's start this problem. And what I'll do is I'll assume current in this direction and current in that direction. Okay. So 1.5 times I minus V1 over 3 is the current through that from that 1.5 source. Then we're going to add to it the 1 amp test source that we have. And that's going to be equal to V1 divided by 2. Sure. We'll forget that that even existed. How's that? So to get this current going in here, I take the voltage drop, the plus to minus voltage drop in the assumed current direction, and divide it by the resistance. So the voltage drop across that resistor divided by the resistance is the current into that node V1 from the 1.5 I. 1.5 I minus V1 over 3. Now you're going to say, wait a minute, Paul, 1.5 I, that's a current, isn't it? But look here. That 1.5 I is just giving you a controlling voltage. It's still a volt. It's the controlling variable for a voltage source, not a current source. If that was an arrow pointing in, we wouldn't be able to do this, right? But since it's a plus to minus, which indicates it's a voltage source, we have to do, we can go ahead and do the KVL approach there. Okay. So that's the current in. We also have 1 amp going in that same node. And then the current going out is V1 over 2. Now, I, the controlling variable, well, we know what that is. I is equal to -1, isn't it? Because 1 amp is going in the opposite direction of I. So that means that I is equal to the negative of that current. So what we have, and I'm just going to substitute this over to here. So 1.5 times -1 minus VI over 3 plus 1 equals VI over 2. Okay.
So the I equals -1, you got that from the test source?
Well, I applied a test source of 1 amp. And from my circuit schematic, I see that I, the controlling variable, is going from V1 down, but I want 1 amp is going in the opposite direction. So I get it from the test source, but it could be any value, right? I could put a 5 amp test source or whatever. So I just say, hey, I'm going to let it equal a 1 amp test source, and then it's in the opposite direction. So I'll make it negative. That's all it is. Nothing more than that. And this is the hardest part about circuit analysis. Do you know why? Because I know what you're all thinking. Oh my God, it can't be that easy. I need to make it more complicated. Right? How can it be that easy? No way. It sometimes is that easy. It really is. Most of the time, if you struggle with some of your classes, it's because you're making it way harder than it needs to be. This really is -1 amp. And that's not a put down. I do the same thing. Sometimes we overcomplicate things. It's like, how could it be this simple? Most of the time, it is that simple. Okay, let's continue. So we have 1.5 times -1. So we have -3/2 over 3 minus V1 over 3 plus 1 equals V1 over 2. So I just distributed the 3 and I did fractions because, you know, why use a calculator when you can do fractions, right? So I have -3 over 6 plus 6 over 6 equals V1 times 1/3 plus 1/2, right? See that 5th grade math coming through, all these fractions in there and common denominators. So I have 3 over 6 is equal to V1 times 5 over 6, product over sum, right? Not doing that too fast. So V1 is equal to, whoops, 3 over 5 volts. Which means 6. Right, because the common denominator is 6, 3 times 2. Yeah. So let's check and see. What's 3 over 5 equal to? 0.6. So I'm giving you another tool And in some cases, you know, it's actually easy to do that. Like if you have a physical circuit that you've built, you physically built a circuit and you want to find the Thevenin equivalent, why not go ahead and put a 1 volt or 1 amp test source instead of doing the calculations and physically measure what it is. If you don't feel comfortable, you know, if you don't want to measure, you can measure the open circuit voltage. Sometimes that'll work, sometimes it doesn't work, but you can always put a test source in there and do it, especially again, if you have dependent sources. If you have dependent sources and those controlling variables are based on your load, you would need to put a test source in there, as long as you don't exceed the capability of the piece of equipment that you have. How about this? Since we're experts, let's do this problem again. And so Matt had a really good idea to solve it. Let's see if we can get, well, actually, we don't even need to do, so we wouldn't even bother to do. Hold on, let me think. Do I want to do that? No, I don't want to do that here. I don't want to do a test source because we already know what the parameters are. So there really isn't any advantage to doing that on this one. Right, because we can know that it's 5K. There's no real reason to do that. So. All right, last thing. We love ourselves some math, right? Is max power transfer. What does max power transfer say? Yes, sir?
R load is equal to R, the source resistance, you get the maximum power out.
Max power transfer occurs. That's exactly right. It's not when it's 0, because there is no max power transfer, right? Because V squared over R or I squared times R, right? When R is equal to 0 is not going to get you anything, right? So you actually have the ability to calculate that. And we have a very simple circuit here, a Thevenin equivalent, which has a VS, an RS, and an RL, right? And all we want to do is we want to prove max power transfer, okay? So how do we know what that is? And you can take a look. I actually have that spelled out over here. So you don't have to look at all the chicken scratches over there. We'll actually just start with a series circuit and then we'll do some math on it. All right, so the first thing we're going to do is solve for the current in the series circuit, which hopefully I'm not pushing everybody's understanding too much. VS divided by RS plus RL is the current through the series circuit. And I'm going to use I squared R, and I'm going to substitute in my I squared, my I, which I just solved for, VS over RS plus RL. So I'm going to square that term. Then I got to do a little bit of math. And you know, like that. All right, let's do it this way then. Well, let's bring it over to whiteboard. And we can see that that's going to be equal to VS squared over RS plus RL squared times RL. How about that, right? Take one of the terms away. Now, let's just look at this equation. I want to solve for when PL is at its maximum. How do you know what PL is at its maximum? Or minimum. I gave you a big hint. How do I know this ugly graph that I just did? How do I know when I'm at a maximum or a minimum? Yeah, if the slope here is 0, or here, or here, or here, or here, that means I've reached a maximum or minimum point, right? That's how you can always tell. So if I take the partial derivative of PL with respect to RL and set that equal to 0, then I can solve for the max or the min. Everybody know what partial derivative means? Anybody know what it means? What that? So it's really unfortunate that and this is not a blaming thing on our math department, but in engineering, we use the term partial derivative a lot. Because you're trying to see the change of something relative to one variable or one parameter being allowed to change. So a partial derivative is just a derivative where RL is allowed to change. And everything else is constant. So RS over here, you don't have a variable there. It's a fixed number from the perspective of a partial derivative. So it is not changing. Okay. So we need to take the partial derivative of VS squared over RS plus RL squared times RL with respect to RL. And then we'll set that equal to 0, and we'll go ahead and do that. So we know that VS squared is a constant, so we can move that out front. So that just becomes 1, right? So if I change my equation, I really get that, correct? So hopefully it makes that a little bit easier to solve. So that's equal to VS squared. What's the partial derivative of a fraction with terms in the numerator and terms in the denominator that you take derivative of? What rule do you use? You all remember this from Calc 1? Quotient rule, right? The quotient rule, which says the partial of a fraction, the derivative of a fraction, which has a numerator or denominator, is equal to the derivative of the numerator times the denominator. Let's do capital D so that doesn't get confusing. Minus the derivative of the denominator times the numerator all over the denominator squared. Do you remember that from Calc 1, most likely? So that's going to be equal to 1 times RS plus RL squared, right? Minus 2 times RS plus RL times RL all over RS plus RL squared. And that equals to 0. But since it's equal to 0, I multiply both sides by this crazy denominator, and then that goes away. So what I'm left with is RS plus RL squared minus 2RSRL minus 2RL squared, and that equals 0. So this becomes RS squared plus 2RS. I put RL, sorry about that, plus RL squared minus 2RL RS minus 2RL squared equals 0. Those terms will cancel. I'm left with RS squared plus RL squared minus 2RL squared equals 0. RS squared minus RL squared equals 0. RS squared equals RL squared. RS equals RL. Everybody's like, what? What did he just do? Just wanted to show you the math. It actually is all here. I'm not expecting you to write it, but that's basically what we did right here. You can see how I expanded out. And you got those terms there. I just did a little bit with factoring, but either one works perfectly fine. So max power transfer is just math. It's just a math equation to get you the answer. That's all it is. Again, the other thing that's really useful about max power transfer is more sophisticated, more advanced circuit analysis. When you're trying to look at something, what we do is when we look at, in my machinery class, we want to look at when the machine is capable of putting out maximum torque. When does maximum torque occur? when maximum power transfers occur. So you use the maximum power transfer theorem to actually help you use that. So superposition, max power transfer, some of those equations are just reserved for later, more advanced math or more advanced circuits topics. But the reason why I think it's worthwhile to go through this is, I hate to just wave my hands, which is probably what you've done in the past. It's just like, here's the answer. It's like, how did you get the answer? Well, just take it from me that this is what the answer is and it's right. And, just memorize it that way instead of actually like, where does it come from? So sometimes it's hard, like this was a fair amount of calculus to get it to get the answer, but it's not impossible calculus, right? So sometimes it just gives you an appreciation of how to actually find that stuff. I think this is my last slide. Yes. Questions on any of this material? Because next class, we'll probably start moving into new material, and then we got to start talking about an exam. Well, it would either be next Friday, not this coming Friday, but next Friday, or the Friday after that.
In lab?
It would be during lab period, yeah. The preference is, because I have a class called EET324, and I think there's probably half a dozen or a dozen of them in both classes. So they have an exam next Monday, and they probably would prefer not to have two exams in the same week.
Yeah.
I won't give you any names as to who said no, but you get the idea, right? That there are more than one that are doing both. Like there's 4 in this class right here, right now. But you don't have to decide today. You can decide, we can talk about it on Thursday. I can adapt and adjust. So we'll pick up a new material, which is RLC time constants, first order circuits. Again, that's probably been some review, but we'll do it slightly differently. We'll start to derive time constants where they came from using differential equations and just simplifying the differential equations, especially for first order one, and then go from there. So any questions, TV land or? So this coming Friday, Mark's going to do just a information session, like just to review practice problems, that type of stuff this way.
So no, there's no actual.
No actual lab. You're not ready for the next lab material.
Okay.
So you actually have a study session essentially.
That's awesome.
Can you hold on? One of your classmates has a question. Yes.
That's something about like a career fair in October then.
October 22nd. Yes. Yep.
Where can we find like one?
If you go to the umaine.edu Career Center, that's where the information is. Highly suggest you get a resume ready. I'm assuming you have one, but you can go to the Career Center and they will actually, you can have a meeting with somebody who will help you tweak or adjust your resume. So get it ready to go, have some hard copies. The best thing you can do is have a few companies that you're specifically interested in, and then you can target them for internship opportunities. There already is, yes. I think there's 138 companies. Well, we can look real quick. Whoops, what happened? Just typed Edge and it disappeared. You also should set up an account with the Career Center. They have another thing to log into, but there it is right there. This is a big deal, and I feel kind of bad because the campus has a lot more than computing and engineering, but this is front page, right, with all the different ones. And so you can see there are Blackboard resources, which is this career link, and it tells you all the different information. So like I said, that's employer registration page. If you log into Career Link, I don't know if I'll try, but I don't think I can log in. It actually will tell you there is a website. I just can't remember where you can find. Yeah, I can't remember where you can find it, but the last I saw, there was 130 something companies. So it's over at the rec center and it's packed. Like it's a chaotic, it's a very hard day. It's loud in there. So you really have to be prepped. This also applies for people in TV land. Even if you're doing the remote class, I highly encourage you to show up on campus, take the day off. It's worth it. October 22nd is when you'll have probably the best opportunity to have FaceTime with some prospective employers. And, you know, you can do, like I said, if you can get the information on the job fair, the MCEC job fair, it has so much information, but I think you have to do it through career link. You have to log in and then you can find out, and then you can actually find out the different companies that they have. So all of you should be hoping to get interns this coming summer, because your internship is a trial job. There's a couple of upper class folks that are in our program, and they came back to school with full-time offers already in hand. So you know how much interviewing they need to do? None. They've already got offers. They're already employed. So they don't have a stressful senior year other than taking classes. Their job is locked up. And the nice thing is you can do it based on geography. Like I know you're in the southern part of the state, you may want to go back there for the summer, but that doesn't mean you can't try something here. You can't try something in central Maine, or you can't go into any place, New York. We've had one of the really ones that I highly recommend if you really want to do the industry I do, which is called ISO New England. And if you go to careers, they have a wonderful internship program. I mean, it is so good. And they're in Holyoke, Mass, which is over by Springfield, Mass, if you're familiar. But they're specifically going to check out career fair and college visits. They used to come to UMaine, but they haven't had a ton of folks that have gone and worked there. But here's their summer internship program, and it's really amazing. And they pay you really well. I think it's $32 an hour. But you got to have a place to live, right? So there you go. 11-week paid internship. Field trips. Lunches with executives. Countless opportunities. And what they're looking for, and I know they hire EETs because we have a bunch of EETs that work there. They just want to see that you have an interest in it. But again, it's about 5 hours from Orono. So if you're familiar at all with Mass, it's Western Massachusetts. It's an interesting area. You're in the Berkshires, I think is what they call it. Western Mass, it's mountainous. So it's not like Boston. It's very different. Has a different feel, but it's a long way from home. So something to think about. So that's the engineering job fair. Got to get on it. Resume, getting spiffy, look presentable. Don't have to wear a suit. Just wear a nice shirt and maybe a tie. And this is not meant to be sexist. I don't know what's appropriate for women, so you can
I'll figure it out.
talk to Jude or talk to the career center. I don't know. I mean, I don't think you have to wear a dress. You can just wear nice slacks or whatever you're comfortable with. You don't have to wear stilettos and all that stuff. You just be comfortable. They're looking for engineers, practical. So whatever, is appropriate. But for boys or men, I should say, I'm going to stop talking because I'm not trying to be gender stuff. I don't know, but I will just say, how about general? Just have a nice collared shirt. Okay. Long sleeve, typically. So don't show off your new tattoos or anything like that. Have dress pants, decent pair of shoes. If you have a beard or whatever, try to be clean shaven, comb your hair, don't wear a hat. That's about it. Don't show up with your Megadeth and AC/DC t-shirt. It probably will have a different opinion on things. You're not going to the club, you're going to try to impress professionals. They're all going to be wearing like business casual stuff. So. Anything else? Oh, we got some chats here. Yeah, sorry, Arthur. You got to just interrupt and let me know, but okay. That's all I have. Have a great day. I will see you all on Thursday. Take care, everyone.
Okie dokie, thank you.
Thank you.
Thank you.